Continuing on in the bonding chapter, we'll examine the ionic bond. First, we'll look at the electron configuration and size of ions, then the energy effect of forming binary ionic compounds, and finally the partial ionic character of covalent bonds. Now keep in mind that atoms in stable compounds usually have a noble gas electron configuration. When two nonmetals react to form a covalent bond, they share electrons in a way that completes the valence electron configurations of both atoms. When nonmetal and representative group metals react to form binary ionic compounds, the ions form so that the valence electron configuration of the nonmetal achieves the electron configuration of the next noble gas atom. The valence orbitals of the metal are emptied so that it appears like the preceding noble gas. This allows us to predict formulas for ionic compounds for many elements on the periodic table. For example, most of our group 1A elements, except for hydrogen, which is a nonmetal, will lose one electron to form a 1+ ion. Our group 2A alkaline earth metals will lose 2 electrons to form a 2+ cation. Aluminum will lose 3 electrons to form a 3+ cation. The group 6A elements will all gain 2 electrons to form a 2- anion. The group 7A elements will all gain 1 electron to form a 1- anion. The noble gas electron configurations attained for each of these elements is shown on the far right. Hydrogen usually acts as a nonmetal and accepts 1 electron to form the hydride, H-. There are several exceptions. Transition metals that form multiple ions don't always have to have 0 electrons in their valence shell. Ion size is important in determining structure, stability, properties, and biological effects of ionic solids. It's impossible to define ion size precisely. There are, however, trends in ion size which are very definite. In general, we see that cations form by removing electrons, and so cations are smaller than their parent atom. Anions form by adding electrons, and so are larger than their parent atom. If we look at size of atom in relation to position on the periodic table, we'll see that as we go down a group, the ionic size increases. The trend across a period is more complex, and so we can't define the trend across a period as well, because on one side of the periodic table we're losing electrons, and on the other side of the periodic table we're gaining electrons in forming ions. We can, however, look at an isoelectronic series of ions, which are ions containing the same number of electrons. Here, the oxide ion, the fluoride ion, neon, the sodium ion, the magnesium ion, and the aluminum ion all have the same number of electrons. They all have 10 electrons. The electrons in the valence shell are the same, but the number of protons in the nucleus increases. Thus, pull on electrons increases and size decreases. In general, for an isoelectronic series of ions, the size decreases with increasing nuclear charge. So we've seen that the periodic table allows us to predict many properties. We've seen that we can look at trends for atomic size, ion radius, ionization energy, and electronegativity. We can come up with electron configurations. We can use the periodic table to predict formula for ionic compounds. And we can use the periodic table to rank covalent bond polarity. Now let's look at some energy effects in the formation of binary ionic compounds. First, let's think about the factors that influence the stability and structures of solid binary ionic compounds. Now, how strongly the ions are attracted to each other in the solid state is indicated by the lattice energy, the energy released upon forming a solid lattice. Lattice energy is the change in energy that takes place when separated gaseous ions are packed into an ionic solid. It's the energy released when an ionic solid forms. So, lattice energy can be expressed using a modified version of Coulomb's law, where K is a proportionality constant, Q1 and Q2 are ionic charges, and R is an interatomic distance. If we look at the formation of lithium fluoride from elemental lithium and fluorine, first it requires 161 joules of energy to take lithium from the solid state to the gaseous state in the sublimation of that solid. In order to ionize lithium in the gaseous state, it requires 520 kilojoules. To dissociate fluorine, molecular fluorine, into fluoride atoms requires 77 kilojoules of energy. The formation of the fluoride ion, the ionization energy, is exothermic at negative 328 kilojoules. So far, everything else has been endothermic. And finally, the solid formation of lithium fluoride from lithium ions and fluoride ions in the gas state releases 1,047 kilojoules of energy. It's exothermic. This is the lattice energy. Overall, the formation of this solid is exothermic by 617 kilojoules. That is mainly due to the highly exothermic lattice energy upon formation of the solid. Here is the structure of lithium fluoride salt. Note the alternating lithium ions and fluoride ions in a close packed structure. All salts of alkali metal and halogens except for cesium salts have this same structure. This is often referred to as a sodium chloride structure. Now we've seen that there are three possible types of bonds. We can have an equal sharing of electrons between identical elements, as is shown by the fluoride molecule in A. We can have an uneven sharing. A results in a purely covalent bond. We can have an uneven sharing of electrons, as is shown in B, between hydrogen and fluorine in hydrogen fluoride. Here we have a polar covalent bond, and we can have a full transfer of electrons, as is shown in C, where we form ions and have an ionic bond. We can calculate how ionic a bond is. Keep in mind that no bonds reach 100% ionic character, even with compounds that have the maximum possible electronegativity difference. Here, our percent ionic character of a bond is the measured dipole moment of xy divided by the calculated dipole moment of xy ionic solid times 100%. If we look at percent ionic character versus electronegativity difference, we'll see that ionic character increases with electronegativity difference. There are no 100% ionic compounds. We consider anything greater than 50% to be an ionic solid. Keep in mind that this is for gas phase molecules where discrete XY molecules exist. In the solid state, things are different because of multiple interactions. In general, we can call an ionic compound any compound that conducts electrical current when melted.